Okay, we're going to introduce the idea of equilibrium here, chemical equilibrium. Right, so and I'm going to use this as a kind of example reaction, the reaction between hydrogen gas and iodine gas, forming hydrogen iodide. It's going to be 2 hydrogen iodide, and that's gaseous as well. Okay, so if you start off with hydrogen and iodine down here, and you allow them to react. So up here we've got the percentage of them that's reacted. Well, as you can see, the amount used up increases, and you might expect this to sort of carry on up here until 100% of the hydrogen and the iodine have reacted, and it's all turned into the products. But that doesn't happen. It seems, about here, that the reaction, so maybe a bit further, just about there. So it seems as though the reaction grinds to a halt. In actual fact, it hasn't stopped at all. Let's see what has happened. Right, so let's look at this. Normally, we don't have that arrow, single arrow there for an equilibrium reaction. We put a double-headed arrow like that. And that shows that the reaction can go forwards and backwards, okay? And what's happening at this point here, we say equilibrium, so about that time there, equilibrium has been established about there. And at that point, you're forming hydrogen iodine constantly all the time. You're forming, hydrogen iodide all the time constantly. But at the same speed, hydrogen iodide is falling apart back into the hydrogen and the iodine. And that's why it seems as though nothing's happened, because the rate of the forward reaction is equal to the rate of the backward reaction. So 2 characteristics of when you have something at equilibrium, and they quite often ask this, are 1, the concentration of reactants and products doesn't change, stays the same. And secondly, the rate of the forward reaction is equal to the rate of the backward. Okay, so if we imagine what's happening, let's have a look at this part of the graph here. Let's have a look. So early on, the forward reaction is happening at a faster rate than the backward reaction, so the amount of product of hydrogen iodine existing is falling. By the time you get here, the rate of the forward reaction is only marginally faster than the backward reaction, and the backward reaction is caught up by the time you reach equilibrium about here, and the rates are the same as each other. Okay, and so what you'd have at this point, you have something called an equilibrium mixture. And I'll just draw this. I'm drawing a picture of what you've got there. So this is supposed to be H2. This is an HI molecule, and that's an I2 molecule. So the equilibrium mixture contains all 3 gases, and the concentration of the gases doesn't change, it remains the same. But that sort of hides the fact that constantly it's not this, although you have the same proportion of hydrogen there all the time, it's not the same molecules of hydrogen. There's different ones all the time. They're constantly changing. They're reacting to form hydrogen iodide, and the hydrogen iodide molecules are reacting together to fall apart and to form iodine and hydrogen. Okay, and the name for this, it's usually called a dynamic equilibrium. Dynamic means moving. It's moving all the time. You can't see it moving. It appears as though nothing's happening, but it is moving backwards and forwards all the time. We could also have a little think about what would happen to if we started off with hydrogen iodide here. So the same thing would happen. You would first of all, the hydrogen. If I draw in a different color, so this is the amount if we start with HI, the amount's going to go up. Sorry, the amount reacted is going to go up, but very quickly it's not going to change anymore. It doesn't all react, so they get 100%. It never gets it to 100%, and that's because the backward reaction is happening at the same time.